What if the most chaotic, unpredictable, and downright weird part of our universe wasn't a flaw to be overcome, but was actually the secret to creating perfect, unshakable order? What if, to build the most powerful machine in history, you didn't have to fight against the laws of physics, but instead, you had to learn how to tie a knot in the very fabric of reality itself? On February 19, 2025, in what was expected to be a standard corporate presentation, Microsoft didn't just announce a new product. They pulled back a curtain on a new reality. They unveiled a quantum processor named Myerana 1, built not on silicon and logic gates, but on a completely new state of matter. State of matter so exotic, it was once considered a mathematical ghost. This wasn't just an upgrade. It was a thunderclap that echoed through every laboratory, boardroom, and government agency on the planet. In a single moment, the entire landscape of human computation, and perhaps human potential, was redrawn. Because Microsoft claimed they hadn't just built a better quantum computer. They had solved the one core soul-crushing problem that has held the entire field captive for decades. This is the story of that breakthrough. It's a story of a 17-year gamble, a journey into the deepest, strangest corners of physics, and a radical idea that could elevate our civilization to a level we've only ever dreamed of. So, settle in, because we're about to unravel the story of Majorana 1. To understand why Microsoft's announcement was so earth-shattering, you first have to understand the fundamental tragedy at the heart of quantum computing. For years, brilliant minds at places like IBM, Google, and INQ have been building these incredible machines. You've seen the pictures, the magnificent chandelier-like contraptions of gold and brass, cooled to temperatures colder than the deepest void of space. Inside these machines live the building blocks of the quantum age, qubits. Unlike a classical bit in your phone or laptop, which is either a 0 or a 1, a simple on or off switch, a qubit is a creature of pure potential. It can be a 0, a 1, or, thanks to a principle called superposition, it can be both at the same time. Think of it this way. A classical bit is a coin lying flat on a table, either heads or tails. A qubit is that same coin, spinning in the air, a shimmering, blurry circle of possibility, containing the potential for both heads and tails simultaneously. It's this both-at-once ability, multiplied across many qubits, that gives quantum computers their godlike processing power. They can explore a vast landscape of solutions to a problem all at once, while a classical computer has to trudge through every single path, one by one. But here is the tragic flaw, the Achilles heel of this entire endeavor. That beautiful, spinning coin is unbelievably fragile. The very act of looking at it measuring it forces it to collapse into a definite state, either heads or tails. Its magical potential vanishes. And it isn't just a deliberate measurement that does this. The universe itself is constantly looking. A stray photon, a tiny vibration in the floor, a subtle shift in a magnetic field, any whisper of noise from the outside world can cause the qubit to fall out of its delicate quantum state. This collapse is called decoherence, and it is the monster that haunts every quantum physicist's dreams. It's like trying to build the most intricate, complex sandcastle in the middle of a hurricane. The environment is constantly working to erase your creation. To combat this, the entire industry has been locked in a brutal war of attrition. Their strategy: brute force, error correction. The idea is to take a single piece of quantum information, our logical qubit, and encode it across a huge number of physical qubits. If one or two of those physical qubits get knocked over by decoherence, the others hold enough information to rebuild the original state. It's a clever strategy, but it's monstrously inefficient. The numbers are staggering. Current projections suggest that, to get just one perfectly stable, reliable, logical qubit, you might need 1,000, or even 10,000, fragile physical qubits to serve as its life support system. This has been the central dogma of the quantum race. Build more qubits, build better shielding, and prepare for a future where quantum computers are colossal, city-sized cathedrals of error-correcting hardware. It was a race to see who could build the biggest, most complex cage to protect the most fragile thing in the universe. And then, Microsoft stepped on stage and told the world they had found a way to let it run free. Microsoft's solution was so radical, so elegant, it felt like it came from a different school of thought entirely. Because it did. Instead of throwing more and more engineering at the problem of decoherence, they went back to the drawing board of fundamental reality. They turned to a field of pure mathematics, one that seems completely disconnected from computing: topology. Topology is, in essence, the study of properties of shapes that don't change when you stretch, bend, or twist them, so long as you don't tear them or glue them together. The classic example is a coffee mug and a donut. To a topologist, they are the same object. Why? Because they both have exactly one hole. You can imagine molding the clay of a coffee mug, squishing the cup part and enlarging the handle until you have a perfect donut shape, all without ripping it. The one-hold-ness is a topological property. It's an inherent protected quality of the object's shape. Now, think about a piece of rope. If you lay it in a straight line, its state is simple. If you tie a simple knot in its a basic overhand knot, you have fundamentally changed its topological state. Here's the magic. You can now shake that rope. You can stretch it, you can bend it, but the knottedness remains. The only way to undo the knot is to perform a very specific action: untying it. The information, the fact that this rope is knotted, is stored not in the position of any single fiber of the rope, but in the global, twisted structure of the rope itself. It's naturally protected from random jostling. This is the core of Microsoft's idea. What if you could store quantum information not in a fragile, spinning coin, but in a topological knot? What if the quantum state wasn't a delicate property of a single particle, but a shared, robust property of an entire system, protected by the very laws of geometry and space? To do this, they had to find a physical way to tie these knots at the quantum level. And that led them to one of the most mysterious and ghostly particles ever theorized. The Majorana, predicted by the brilliant physicist Majorana in the 1930s, before he mysteriously vanished. These are bizarre, exotic particles. In the quantum world, every particle has an antiparticle. An electron has a positron, for example. When they meet, they annihilate each other. But a Majorana fermion is its own It's a particle that exists on the razor's edge between being and non-being. For decades, they were purely theoretical. But Microsoft's team believed they could coax these ghosts into existence. Not as free-flying particles in a vacuum, but as quasi-particles, emergent phenomena that appear at the ends of special superconducting wires, like the two ends of that knotted rope. The quantum information wouldn't be stored in one of these Majoranas, but would be encoded in their relationship to each other. You could have two of them, and their combined state could represent a zero. Braid one around the other, literally tying a knot in spacetime, and their combined state would now represent a 1. Because their existence is tied to the fundamental topology of the material they live in, this state is incredibly robust. The universe can't just accidentally look at one of them and destroy the information, because the information doesn't live in any single one. It lives in the knot. It's an inherently protected qubit. This beautiful, elegant idea was also, for a very long time, considered scientific fantasy. When Microsoft began its formal quest for a topological quantum computer in the mid-2000s, the community was deeply skeptical. The dominant approach's superconducting loops and trapped ions were already producing tangible, if fragile, qubits. Microsoft's path seemed like a quixotic quest for a mythical creature. It required inventing and fabricating entirely new forms of matter that had never existed before on Earth. Their journey was a 17-year odyssey of immense investment, crushing setbacks, and quiet, persistent faith. Billions of dollars were poured into what many outside the project saw as a black hole. Their goal was to create a material they called a topological substance that was simultaneously a superconductor and a topological insulator. Think of it as a material that's a perfect conductor of electricity on its surface, but a perfect insulator on the inside, with bizarre quantum effects happening at the boundary. It's like baking a cake where the crust is a superhighway for electrons, but the inside is a complete roadblock, and magic happens right where they meet. After countless failed attempts, they finally engineered it. They started with incredibly thin aluminum nanowires structures, thousands of times thinner than a human hairend, coated them with these exotic topoconductor materials. The real breakthrough came in the design. They didn't just use straight wires. They arranged them into intricate, H-shaped structures on a chip. Picture one of these H's. At the four endpoints, the top and bottom of each vertical line, the specific physics of the topoconductor would coax a single Majorana fermion into existence. These four ghost-like particles, anchored to the physical structure, would form a single ultra-stable unit. The quantum information, the O south and 1 south, would be encoded by braiding the world lines of these particles around each other. They had built a microscopic loom for weaving the fabric of spacetime. This wasn't a journey of one single eureka moment. It was a slow, agonizing process of ruling out a million things that didn't work. It was about achieving atomic-level precision in manufacturing, battling against microscopic impurities that could shatter the delicate quantum state they were trying to create. It was about the theorists arguing with the experimentalists, the years of data showing nothing, the papers published by rivals claiming that the Majorana signals others had seen were just noise. Through it all, Microsoft's leadership held the line, making a colossal bet that elegance would ultimately trump brute force. When the first results from Myerana 1 started coming in, the team at Microsoft must have felt a mix of exhilaration and terror. The numbers were too good to be true. Quantum computers are judged by their coherence times. The length of time a qubit can hold its quantum state before For traditional systems, we're talking about microseconds, maybe milliseconds, on a very good day. A blink of an eye is an eternity. The topological qubits in Myerana 1 were demonstrating coherence times orders of magnitude longer. The data they were storing was simply staying there. It was like they had finally built a sandcastle that the hurricane couldn't touch. The initial stability was so profound, so far beyond the industry standard, that it immediately raised flags. When Microsoft made their announcement on February 19, 2025, the reaction from the scientific community was not instant celebration. It was a wave of stunned, cautious curiosity. The phrase on every expert's lips was, "Extraordinary claims require extraordinary proof." No one was calling them liars, but everyone was demanding to see the work. The preprint papers were released, and a global race began not to beat Microsoft, but to replicate them. Labs at MIT, Harvard, the Niels Bohr Institute in Copenhagen, institutions that had once been skeptical, were suddenly scrambling to reconfigure their own experiments. Could they reproduce the same exotic state of matter? Could they confirm the existence and control of these Majorana fermions in the H-shaped structures? This is the crucible of science. A discovery is not real until it can be independently verified. The entire quantum world held its breath, waiting for another lab to see the same ghost. The pressure was now on the rest of the world to prove that this wasn't just a fluke, but a fundamental turning point in our mastery of the quantum realm. As the weeks turned into months, and whispers of successful replications began to emerge, the geopolitical and industrial implications started to sink in. The quantum race had been, up to this point, a marathon where everyone was running on the same track, just at slightly different speeds. IBM and Google were in the lead. Their strategy built on the brute force model of scaling up massive numbers of increasingly better, but still fragile, superconducting qubits. Microsoft's Myerana 1 was the equivalent of one runner suddenly revealing they could fly. Their approach didn't just make other systems look less efficient. It threatened to make them conceptually obsolete. The colossal investment in massive-scale error correction now looked like a potentially dead-end path. Why spend billions building a billion-qubit error-correcting computer to yield 1,000 logical qubits, if a topological machine could potentially yield 1,000 stable logical qubits with just 1,000 physical ones? The shockwave hit the financial markets first. Venture capital that had been flooding into dozens of quantum startups suddenly paused. Investors began redirecting their funds, desperately looking for anyone with expertise in topology and Majorana physics. A new gold rush began. Governments, who view quantum supremacy as the 21st century's equivalent of the space race or the nuclear bomb, were thrown into a panic. The US, China, and the European Union had all invested billions in their national quantum initiatives, largely following the mainstream path. Now, they were facing a topological gap. A furious reallocation of resources began. New research programs were funded overnight. Scientists who had been toiling in the obscure corners of topological matter theory suddenly became the most sought-after experts in the world. The balance of power in the global technology race had been fundamentally disrupted. The nation that could master the fabrication of these exotic topological computers wouldn't just lead in computing. They would lead in everything. So, what does a world with scalable, stable quantum computers actually look like? Why are governments and corporations willing to spend fortunes to build them? The answer is that this technology doesn't just make things faster. It makes the impossible possible. Let's start with medicine. Today, discovering a new drug is a decade-long, billion-dollar process of trial and error. We're essentially guessing which molecules might interact with a disease. A topological quantum computer could simulate the exact quantum interactions of a complex protein, like one on the surface of a cancer cell or a virus. A chemist could then, on a screen, design a drug molecule that fits into that protein like a perfect key in a lock, deactivating it with surgical precision. We could design personalized cancer drugs in an afternoon. We could create cures for Alzheimer's by simulating the misfolding of proteins in the brain. The era of guesswork in medicine would be over. Then there's materials science. We could design a material, atom by atom, that superconducts electricity at room temperature. This would mean lossless power grids, saving enormous amounts of energy. It would mean ultra-powerful magnets for things like maglev trains and medical imaging, all without the need for extreme cooling. We could design catalysts that pull carbon dioxide directly out of the atmosphere to reverse climate change, or fertilizers that are perfectly efficient, ending agricultural runoff and revolutionizing the food supply. In finance, markets could be modeled with a fidelity that accounts for the chaotic, unpredictable nature of human behavior, potentially preventing economic collapses. Climate science could move from prediction to precise simulation, allowing us to test solutions for global warming in a digital twin of Earth before deploying them in the real world. And then there is the most profound application of all: artificial intelligence. Today's AI is powerful, but it's based on classical probability. Quantum machine learning, powered by stable qubits, could explore possibilities in a way that's fundamentally different. It could lead to is with an intuition and a creative problem-solving ability that mimics, or even surpasses, our own. It would be a new kind of intelligence, born from the same quantum weirdness that underpins consciousness itself. The implications are staggering and, frankly, a little terrifying. For all its world-changing promise, Myerana 1 is not the finish line. It is the discovery of a path up a mountain that was previously thought to be The journey to the summit is still fraught with immense challenges. The first is scaling and fabrication. Creating the exotic materials for these topoconductors requires a level of precision that makes traditional microchip manufacturing look like blacksmithing. We're talking about depositing layers of atoms with perfect crystalline structures in environments of absolute purity, all while cooled to a fraction of a degree above absolute zero. The infrastructure required to do this on a mass scale does not exist yet. We will have to invent entirely new fields of manufacturing and cryogenics. The second challenge is control. While topological qubits are great at storing information, we still need to perfect the methods for manipulating it for performing the quantum gates, the braiding operations that constitute a computation. This is a monumental engineering task, requiring new hardware and new algorithms. And finally, there's the ongoing need for proof. Critics and skeptics rightfully remain. The scientific method demands rigor. The world will need to see not just one Myerana 1, but hundreds of them, built by different teams in different countries, all demonstrating the same unprecedented stability. Microsoft has shown the world the blueprint, but now they and others must prove it can be reliably They have solved the great physics problem. Now, they face an equally great engineering problem. As one physicist famously quipped, climbing Mount Everest is one thing. Building a city on the summit is another. Ultimately, the story of Myerana 1 is about more than just a computer. It represents a fundamental shift in our relationship with the universe. For most of human history, technology has been about imposing our will on the world. We build dams to fight rivers. We build stronger materials to fight gravity and pressure. Even in traditional quantum computing, the approach was to fight the universe's tendency toward decoherence, to build a fortress against the noise of reality. The topological approach is different. It's a technology of partnership, not of conflict. It's about finding the hidden, elegant structures within the laws of physics and using them to our advantage. It's realizing that the very weirdness of quantum mechanics, the entanglement, the non-locality, the ghost-like particles aren't bugs to be shielded from. They are features to be harnessed. This breakthrough forces every researcher, every company, every nation to reevaluate their strategies. It ignites a new fire under a generation of young physicists and mathematicians, opening up entirely new fields of research. It accelerates our timeline for tackling some of humanity's grand challenges: disease, energy, climate change. We are seeing a transition from a paradigm of brute force to a paradigm of elegance. And that philosophical shift may be the most important product of Myerana 1. It teaches us that sometimes the most effective way to solve an impossible problem is not to build a bigger hammer, but to find a way to tie a knot. So what does this story of ghost particles and quantum knots mean for you in your daily life? First, it's a powerful lesson in the value of long-term vision. In a world that often rewards quarterly profits and immediate results, Microsoft's 17-year bet on an unpopular, esoteric idea is a testament to the power of patient, persistent belief in a revolutionary concept. It reminds us that the greatest breakthroughs rarely come from taking the easiest, most obvious path. Second, it's a lesson in embracing different ways of thinking. When the entire industry was trying to solve the problem of fragility with brute force, more shielding, more error correction, the topological team looked to the elegance of mathematics for a different kind of solution. It's a prompt for all of us. When you face a persistent problem in your life or work, is there a topological solution you're not seeing? Is there a way to restructure the problem itself so that the solution becomes inherent and stable, instead of constantly needing to patch it and prop it up? The quantum revolution, as this story shows, is no longer a distant, abstract concept. It has begun. And it's a revolution that will be built not just on engineering, but on a deeper understanding of the beautiful, strange, and powerful reality we all inhabit. I want to leave you with a couple of questions to think about. If this technology were available to you today, right now, what is the one problem in the world, or in your life, that you would want to solve with it? And what do you believe is the most important thing our society needs to do to prepare for the changes, both good and bad, that this level of computational power will bring? Let me know your thoughts in the comments below. I'm genuinely curious to hear what you think. Thank you for joining me on this incredible journey into the future. I hope it sparked your curiosity and gave you a sense of the amazing world we are on the verge of creating. And if this story sparked your imagination and you want to keep exploring the frontiers of science and technology, please consider subscribing to the channel and turning on notifications. It really helps us continue to bring these stories to you. We'll see you in the next one.